All right. The next two problems are dual to each other. In this problem here, which is E, we start with I equals 2 and square repeatedly until we pass n, until we reach n. While in the other one, we start at n and take the square root repeatedly until we reach 2. So the sequence here, if you look at the values of I here, 2, 4, 16, keep squaring every time. But on this one, we start with n. Let's just pick a random n, 65,536. Take the square root each time till we reach 2. And it's the same number of steps. How many steps is that? Roughly log of n, where say n is 65,536. All right, now let's analyze this. We're going to start by saying j, we're going to let j equal the base 2 logarithm of I. Now, when we do that, what happens? We start with j equal 1, because that's the base 2 logarithm of 2. And then j stops at the base 2 logarithm of n. And then when we square I, we double its logarithm. So j equals 2j here. All right. Now, if we want to know what to do with the next thing, how to do that, we can do another substitution. K equals the base 2 logarithm of j, and then we get for int k equals the base 2 logarithm of 1 is 0, k less than log of n, and then k plus plus, because we're only increasing it by 1. When we double j, we only add 1 to its logarithm. Now, by the theorem I put up on a previous board, in the previous slide, we know that the time complexity of this is theta of log n. But, no, log n. And so that's actually the answer then. That's the final answer. All right, let's go over to this one. Well, we're going to do the same substitution. J equals the base 2 logarithm of I. And then our for loop becomes for j equals the base 2 logarithm of n. J greater than 0. And j equals j divided by 2. All right. Now, we can make the same substitution we did from a previous problem. K equals base 2 logarithm of j. And then we could say for k equals 1, no, k equals log n. For k greater than, well, what's the log of 0? It doesn't exist, so I guess I'm going to have to be stuck with that. And then k plus k minus minus, because I'm decreasing it every time. So we already know that this is a linear for loop, so the answer is theta log n, just like the other one. All right, now, before we start on this problem, the last one here, number G, let's look at this. If we say a summation of powers of 2, 2 to the power of power, notice how fast it goes up. Now, I'm sure you will believe me when I say that the last term overwhelms all the others. And so we have theta of 2 to the 2 to the n here, if we do that. All right, now, that being said, let's go forward to this one. We have, I starts at n, goes down, taking the square root each time, which is familiar with what we did last time. And then L goes up with plus plus. So what is the asymptotic complexity of that? Well, it turns out it's theta of n. That's a little bit odd, but you see, in the first iteration of the outer loop, there are n values of L, because I equals n here. And then in subsequent iterations, there are so many fewer that the n simply dominates, and it's theta of n, essentially because of this summation here. All right, let's go through the formal proof. L is 0, L is of course less than I, and L plus plus. Okay, so now we're going to let j equal log I, which means I is 2 to the j. And so we keep going here, replacing this in j equals log n, right? And then j greater than 0, j equals j over 2. And then what happens here? We're starting with L. L is less than I, but remember I is 2 to the j, and we increment by 1 every time. Well, we're still sort of not knowing what to do with that, so we can make the other substitution. Finally, k is log j, which means that j is 2 to the k. It also means that I is 2 to the 2 to the k. 2 to the 2 to the k. All right, now, let's look at what we have here. For n to k, we're going to replace the j's with k's. K is a log j, so this is log n. K greater than or equal to 0, k equals k minus 1. All right, now, here L is 0, but L is less than what? It was 2 to the j before, but j is 2 to the k. So it's 2 to the power of 2 to the k, increment by 1. Now, by theorem we put up last time, the number of iterations of the inner loop for each k is theta of 2 to the 2 to the k, which means the total number of iterations of the inner loop over all iterations of the outer loop is a summation here like this. 2 to the 2 to the 0, which is of course 2, and then this is 4, and then 16 and so forth until it goes up to the very last term, which is by far the largest, 2 to the log n. All right, now 2 to the 2 to the log n. Now, what happens here is that 2 to the 2 to the log n is nothing but n. So therefore the summation is theta of n. We're now going to consider problems 4 and 5. Problem 4 first. I didn't really like the way I asked these questions. If I do them again, if I have any questions like this on the final, I'll be much more specific. And so it was very hard for me to figure out what people meant when they put down their words. I think what I'll do in the future is I'll give you multiple choice. Is it like A, B, or C, or D? Well, let's look at this. If we want to store an array, there are basically 3 methods that, these are not the only 3 methods, but these are the 3 methods I've introduced to you. First way is to simply store it as a 2-dimensional array using the built-in implementation of array. It's built into most computer languages. For example, if I have an array here, it's 4 by 4, then this representation here that I'm writing would then be the way you would think of it in the computer. All right, now, here we have a different situation where this array is sparse. Most of the entries are 0. Now in this case, instead of storing 25, or let's say n squared positions, we can get by with fewer by simply having an array of only n size, where for each I, we store the non-zero entries in that row. Well, it looks like I missed one here. This is the array in position, let's see, this would be 5, 4 for row 3. So this is the correct thing there. Now, that means there's a possibility that a row will be blank because it's assumed that all entries that are not specified have the default value, which I'm assuming is 0. Now actually the default value could be anything. If it's an array of pointers, the default value could be null. If it's an array of letters, the default value could be blank. But whatever it is, we're going to call it 0 when we talk about it. Now, this is sort of the ultimate going in the other direction. If you have an array where the number of non-zero entries is considerably smaller than the number of rows, you might want to use a situation where you simply separately store each non-zero entry into a single search tree. Not necessarily a search tree, a search structure, which I've written here as a binary tree. There are only 3 non-zero entries here. A of 7, 2 is 6. That's triple. 7, 12 is -2. Of 10, 8 is 1. Well, it looks like I messed up with the binary search tree. I should have this one on that side, shouldn't I? Let me switch that because I don't know. Somebody might be looking at it and get it wrong. So this is 7, 12. Oh, no. This should be at the root here. So this should be 7, 12, -2. And then before that we should have 7, 2, 6, and the next entry would be 10, 8, 1. Now you notice in the search structure, you're indexing by the pair ij, not by the value. The value plays no role in the structure of the search structure here. Alright, now the next question deals with graphs and how they're implemented. As I said, just like the previous problem, if I ask a question like this again, I'll give you multiple choice, like A, B, C. Here's an array, an n by n array implementation, where there's simply a space for every possible, a space in an n by n array for every possible edge. Now, if there's no edge, we need some kind of a default value in here. It doesn't have to be 0. It could be infinity if you're doing minimum path problems. But in any case, you have to somehow indicate there's no edge there. If there is an edge, I'm assuming, by the way, that we have a directed weighted graph. So for undirected graphs, of course, it's simpler. And if there are no weights, you would simply have booleans in here. So what we're doing is putting in an answer for every possible edge, which means n squared entries. So we're assuming this graph is not sparse. You can see it has almost half of n squared non-zero entries. All right, now let's go over here to a sparser graph. This one has 7 edges and way less than 49 edges. I'm sorry, 7 vertices and way less than 49 edges, so it's sparse. And I claim the best way to represent this is with an array of out-neighbor lists. Again, this is directed. And for each vertex, we have to have a search structure here, which could be a simple linked list, an unordered linked list, but it could be a more complicated search structure, and it depends on how many out-neighbors a node has. Here, I'm listing in each of these is an ordered pair, where this gives the index of the edge, of the vertex that the edge points to, and this gives you the value along the edge. Of course, if there are no values, you don't need the second number. So we'll call that an array of out-neighbor lists. Now instead, we could have an array of in-neighbor lists. And if it's not a directed graph, we would simply have an array of neighbor lists. All right, now let's look at the next problem, which is Huffman coding. Now here is an alphabet A, B, C, D, E, F, G, with frequencies for each letter. And what you do is you sort the letters by frequency, and then you perform a sequence of combinations where each step you combine the weights of the smallest two nodes that are don't already have parents, and you write the weight there of the combination. So now in this situation, the smallest two are 9 and 12, because you don't distinguish between those that are already a combination and those that are already isolated. So this becomes a weight of 21. All right, now at this step, we have 13, 21, 15, and 22 are the only nodes we can use. We take the bottom two, which are 13 and 15. And so what do we get here? This would be 28. All right, now we take the bottom two there, which are 21 and 22, and we get 43. And then we can combine these two to get 71. Now you notice I wrote the 28 to the right of the 21. Does that really matter? No, I could have written the 28 to the left of the 21. And so you just have to, there are certain things that don't actually matter. So let's see what happens when we derive a Huffman code from this. This is 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Now, that would give us a code here for A. You start at the top. For A, you get 1, 0, 1, following the trail. For B, you would get 1, 0, no. You would get 0, 0, 0 for B. And for C, you would get 0, 0, 1. Now for D, I would get 0, 1. For E, I would get 1, 1. Now for F, let's see, F is here. Going back there, it would be 1, 0, 0, 0. And for G, 1, 0, 0, 1. All right, now, those strings are not unique. If you ordered them in a slightly different way, you would get a different code. But if the code is optimal, these two will have length 4, these two strings will have length 2, and these three strings will have length 3. All right, now let's go over to the next problem, which is number 7. I wanted you to look at a min heap here. So I first start by giving you a min heap. Now this is the array representation, DFHMLR, which is an implementation of the binary tree representation, DFHMLR, where you write these things in level order. All right, now the first thing we do is we're going to delete the D, which means that we copy the last element into the first place. Now, when you do that, this R in the array doesn't actually get erased, because you don't bother to stop it. What are you going to do? Replace it with a blank symbol? No, you don't bother to do anything. It'll be overwritten later. All right, so that means that the implementation here is that this element is gone, the R is up here, and now we bubble down. Here's the first step. We replace, R is exchanged with its smaller child. And now here, R has to be exchanged again with its smaller child, which is L. So this is the final heap order. The heap order has been restored as we have this array implementation here. All right, what was the next thing we were supposed to do? We were supposed to insert the letter E. So we're going to start by, we start with this tree here, which means we don't need these anymore. And when we insert the letter E, it has to be inserted in the last place. And the last place in level order is the sixth place in the array, which is here, the left child of H. So this is our letter E here. All right, so now what happens here? This becomes F, L, H, M, R, E. Now this, I no longer have the circled in red. Circled in red means that they're not being used. Now we have to bubble up. We bubble up with the E. So it has a parent. This is position 6, so its parent is position 3, and it's smaller than its parent, so it exchanges position with the parent. And we have that situation. Now it's in position 3, its parent is in position 1, and it's smaller than its parent, so it exchanges again. Now if we go over to the picture, we can see that this exchanges up, and we have this binary tree there, and one more exchange with the parent gives us this tree here, which is implemented by this array here. E, L, F, M, R, H in level order.